Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 8, Circles, Angles, and Shapes, Lesson 2, From Polygons to Circles. Starting with the Ready section, the directions here say calculate the perimeter and area for each figure. So the figures in this section, sometimes they're called composite figures because they're just like made up of, I guess, more basic figures. And number one's kind of a classic example of a composite figure. We have a whole bunch of quadrilaterals, and I'm just going to go ahead and assume that these are rectangles. I mean, they're gonna have to be rectangles. So we have three different rectangles. Looks like the middle one's probably a square. And we're being asked to find the perimeter and area. Now, with a problem like this, I think it's a good idea. It's not strictly necessary, but I think it's a good idea to try to label pretty much any side lengths that you can. All right. So I say label everything, and then when we're going to find the perimeter, we're going to choose what we want to include, and with the area, we're going to choose what we want to include. But it's very, very easy to miss something if it's not labeled. So I'd say go ahead and just sort of label anything that you possibly can. So if we take a look at the top rectangle, notice that we have a height of 10. Well, because we have a height of 10 on the right, I'm going to say 10 on the left as well. All right, so opposite sides of a rectangle are congruent. So if the right's 10, then the left is 10. And then likewise, the top is 2.5, so that means that the bottom is also 2.5. 2.5. Now, looking at the middle figure, I think it's safe to assume that we're talking about a square here. So we've got three sides are congruent along with one right angle. There's got to be a property that tells us that that's a square. So what that means is, well, first of all, regardless of whether it's a square, the top is 3.5 plus 2.5, and so the entire length is 6. Now, assuming that this is a square, it means that all of our sides are going to be congruent. So if one of them is 6, that means that this is 6, and this is 6, and this is 6. So all of those are 6. And now looking at the bottom rectangle, well, if the height is 4 on the left, it means that the height on the right is also 4. And then the top is 8 plus 6, which is 14. So that means that the bottom is also 14. So now I've gone ahead and I've sort of labeled any and all side lengths that I possibly can. And now I want to find the perimeter. So in order to find the perimeter, what I want to do is I want to figure out, I want to determine what are all of the side lengths that are on the outside of this figure. So that means I'm looking for the lengths that are sort of between the green space and the white space. Right? So if I were to sort of walk around the edge of this figure without going, inside it, what would be the total distance that I would walk around this figure? So what I'm going to do is I'm actually just going to pick an arbitrary spot. We'll say like that corner. And I'm also going to pick an arbitrary direction. We'll just go like this way. And what I'm going to do is I'm going to go around and I'm going to circle anything that's on the outside. Right? So this 14 is on the outside, 4, 6, 10, 2.5, 10, 3.5, 6, 8, and 4. So notice that I haven't included anything that's on the inside, and I haven't double counted anything, right? Which you also don't want to do. You want to be careful about all of those things. So my perimeter here is simply 14 plus 4 plus 6 plus 10 plus 2.5 plus 10 plus 3.5 plus 6 plus 8 plus 4. So if I add up all of these numbers, it's a 2 right there. If I add up all of these numbers, which I don't think I need to show on the calculator, it's kind of a longer calculation, but it's just, addition. It's just repeated addition. I end up getting 68. And we're not told what kind of units we have here, whether this is, feet or inches or meters or miles or light years or whatever it is that we're talking about. So we'll just go ahead and say units because, this length is 14 units, this length is 3.5 units, and so our perimeter is going to be 68 units. So I'll go ahead and put the answer down here, I guess. So 68 units. There are other ways of getting the perimeter. It actually turns out that if you just sort of treat this as like one big rectangle like this, and you just find the perimeter of that, this would be 20, and this would be 14, and this would be 14, and this would be 20. 20 plus 20 plus 14 plus 14 is also 68. So that is another way of getting the 68. But you just want to be, if you're going to do that method, you're going to want to be real careful. I think it's actually easier to do the slightly more, I guess more complicated, but also easier in a way method of just sort of counting up everything on the outside. But as far as perimeter is concerned, if you treat it as one big rectangle without the gaps, that actually does work for perimeter. That is not going to work for area, however. So with area, we really are going to have to kind of focus on the individual shapes here. For area, the total area of this composite figure is simply going to be the sum of the areas of each individual figure. So again, we've got three rectangles here, and so if I find the area of each individual rectangle and add them up, we will get the total area. So if I take a look at the bottom figure has a base of 14, and it has a height of 4. So that's the area of the bottom figure, plus. The middle figure has a base of 6 and a height of 6. And with a square, the area of a square is also s squared. So 6 times 6 is obviously 6 squared, but we'll write it like this for now. And then the rectangle at the top, my base is 2.5, and my height is 10. And again, I don't think we have to show how to type this into the calculator because it's just, the calculator will do order of operations for us, so we don't even have to worry about that. So if you enter this correctly, you should get 117. And so our area is going to be 117. Now again, we're not given the units, but it is area. So really, we're talking about square units. Because whatever these numbers represent, inches, centimeters, whatever, the area is going to be given in the square version of those units. Square inches, square centimeters. Question number 2. So question number 2, we have a like a donut, or like a two-dimensional cross section of a donut, I guess I should say. And we're told that r equals 4, which is going to refer to the small radius. So this piece right here is 4. And then we also have, make this purple. We also have d equals 18, which is the big diameter. So we have one piece of information for the little circle, and then we have another piece of information for the big circle. We know the radius of the little guy, and we know the diameter of the big guy. They're using the word perimeter here, and we're being maybe a little fast and loose with the terms here. So the perimeter of a circle is commonly referred to as circumference, but I think because it's a composite figure, they're just going with perimeter. And they're pretty clear here that they want both the inside and the outside. So that means they want essentially the sum of the circumference of the outer circle plus the circumference of the inner circle. So we're going to need to find both. So we'll use their terminology of perimeter. For the little circle, we know that we can find the circumference of a circle with the formula 2 pi r. So 2 times pi. And for the little circle, my radius is 4. And the total perimeter means we're going to add. Now I want the circumference of the big circle on the outside. Well, they gave us the diameter, and one thing that we could do is we could take the diameter and get the radius, which is 9, and then plug it into the same formula, 2 pi r. However, there's also another, it's not really a different formula, it's the same formula, just sort of expressed differently. You can also find the circumference by simply taking pi times the diameter. So because we're given the diameter, let's just go ahead and make life easier on ourselves and just say pi times the diameter. And hopefully you guys can see that if you were to take the radius, so the radius is half of 18, which is 9, and then if you plug it into 2 pi r, you're going to get 2 times 9, which just gets you right back to the 18 that we started with. So, if you get the radius and you plug it in, you'll get the same answer, but it's easy enough just to use pi times diameter. So we can clean this up a little bit. Our first term is 2 pi r, 2 pi times 4. So 2 times 4 is 8. And then we can move our 18 to the front. It's kind of the mathematical convention for how we would write that. So we have 8 pi plus 18 pi. In this context, you can treat pi like x, right? So 8x plus 18x is 26x. Likewise, 8 pi plus 18 pi is 26 pi. Again, you just treat it like you would a variable or an unknown. So the perimeter here is going to be 26 pi units. And the directions didn't say how to handle pi. So if we want to get an approximate answer here, we can simply say 26. And if you didn't know this already, pi is actually stored in your calculator. It's above the exponent key on the right. It's in blue. So if you press second and then the exponent key, you get pi. It's a good approximation for pi. And we get 81.68. So 81.68 units. So we have both an exact answer in terms of pi and an approximate answer. And depending on the context, either one of those answers might be most appropriate, but we don't really know what context we're dealing with, so we'll go ahead and write both. And then for the area of green, notice that it's kind of interesting. With perimeter, we ended up adding the two circumferences. We ended up adding the circumference of the outside, and then by sort of cutting out the hole in the center, it created more circumference. It created more sort of barriers between the green and the white. So our perimeter actually increased because of the hole in the center. With area, it's going to have the opposite effect. With area, if you cut out the center, you are subtracting area. So just kind of a interesting way that perimeter and area just don't always behave the same way. So for the area of green, and actually I'm going to erase my work from earlier just to give us most amount of space to work with here. So for area, the area of the large circle. Now with area, we really do want to use radius when we're talking about area. Technically, you don't have to, but if you're going to use diameter, your formula becomes 1/4 pi times diameter squared, and that's annoying. So I would just say get the radius with area, get the radius, and then use the radius. It'll just make your job easier when you're working with area. So the area of the large circle, based on the diameter of 18, well, area is going to be pi r squared. So that means the area is going to be pi. If the diameter is 18, then the radius is half of that, which is 9 squared. And again, with area, we have to subtract the smaller circle because we're cutting out the green that would normally be in the center there. So we're going to subtract the small circle, which again is pi r squared. And this time, my radius for the little guy is 4. So 9 squared is 81, and we move it to the front, we get 81 pi. And 4 squared is 16, we move it to the front, we get 16 pi. 81 minus 16 is 65 pi. Oop, I just did, that was weird, did pi twice. 65 pi. And that is our exact answer. So I'm going to go ahead and put it. So we got 65 pi. And again, area is square units. Square units. Which is, if we want to give an approximate answer, 65 pi gives us 204.20. So this is approximately 204 point, what did I say? 204.20 square units. And this is our answer, both an exact version and an approximate version. Next assigned question was number 4. So for number 4, we have, I guess we have almost a circle. To me, when I look at this figure, it kind of jumps out at me that we have, we essentially have 3/4 of a circle. So we have the top left, the bottom left, and the bottom right of a circle. But then in the top right, you know, it's almost like quadrant 1 if you think about it on the coordinate plane. In the top right, we've sort of cut out our circle and replaced it with a square. Okay. Same idea, though, is we want the perimeter and we want the area. So probably the way to think about this, I think probably the easiest way to think about this problem is to just find each of these things for the 3/4 square and for the area, and then sort of combine them. So for the perimeter, what that means is I want 3/4 of my circumference, because what we're talking about here is we are talking about this piece of the outside of my figure, right? So we want that piece first. So in order to get that piece, well, that's going to represent 3/4 of my circumference. And notice that we are given the radius of the circle. The radius is 24. So it's 3/4 of 2 times pi times 24. That's 2 pi r. Okay? So that alone represents the red piece. Then, in order to get the perimeter of my entire figure, we also need to include this piece right there, because that is also on the outside, and we're going to add that. So we're going to add, well, each side here is 24, and we have 2 of them, so we have 2 times 24. That's what's on the outside. So I can clean this up a little bit. 3/4 of 24 is 18 times 2 is 36. So this first term simplifies to 36 pi. I just did 3/4 times 2 times 24. And again, as a reminder, on the calculator, if you want 3/4, it's just 3 divided by 4. A fraction is just division. That's all that is. So you could do 3 divided by 4 times 2 times 24. You'll get 36. And then don't forget about the pi. And then 2 times 24 is 48. And that is my exact answer. So for my perimeter, we'll say 36 pi plus 48, and they only gave it in a we'll leave it the way it is. So it's this many units, but it might be a good idea to also give this as an approximate answer. So for the approximate answer, so 36 pi plus 48, 36 pi plus 48 gives us 161.10. So the 7 bumps the 9 up, and then the 9 bumps the 0 up. So 161.10. Units. And I guess I'm just arbitrarily deciding to round to the nearest hundredth. It didn't say what to round to, but that's just what I'm deciding to do. Now for the area. Should have enough space here. So for the area, we're going to do something similar in that we're going to just take the area of the 3/4 circle, and we're going to add the area of the square, and that's going to be our total area. So for the area of the 3/4 circle, again, it's going to be 3/4 of, our formula for area is pi r squared. So we get pi times 24 squared. That represents the 3/4 circle, sort of the Pac-Man figure. And then for the area of the square, well, the area of a square is just 24 squared. So 24 squared is whatever that is, times 3/4. It turns out that this is going to simplify to 432 pi plus 24 squared. If you type it into your calculator, you get 576. So my area is 432 pi plus 576. Sorry. This is area, and so now we're talking about square units. That's my exact answer. If I want an approximation, I'm not going to show you. I mean, it's just like what we just did for the last couple problems. If you go ahead and type it in, you should get 1,933.17 square units for my total area of this composite figure. Next assigned questions appear in the set section. And our first assigned problem was number 8. So number 8 says, which polygon has an area and perimeter closest to the circle in which it is inscribed, and why? And our figures are on the next page. So here are our figures. And we're going to describe what's happening here. So let me go ahead and get my text box ready. Nope. All right. So our question is, which figure here has an area and perimeter that is closest to the circle in which it's inscribed? Well, if you remember from the lesson, one thing that we saw is that when you have a figure like this that's inscribed inside a circle, and you can see it here just by kind of looking at it, as the number of sides increases, the regular polygon that is inside the circle, it starts to get closer and closer and closer to a circle. Right? You start with the triangle, and no one's going to confuse a triangle with a circle, so those are pretty different. And then likewise, no one's going to confuse a square with a circle, although compared to the triangle, the square kind of looks more like a circle, sort of. And then going to the pentagon, okay, yeah, I can see it starting to look like a circle. And then when you hit the hexagon, well, now you can really start to see what's happening here as the sides increase. And then with the octagon, there's barely any white there at all, and with the decagon, it's really starting to look like a circle there. So the polygon that has an area that's going to be closest to the circle is going to be polygon F. Now, why is that true? So F has the largest number of sides. A through F, it has a large number of sides. Specifically, it has 10 sides, right? So it's a decagon. Of all the figures And as the number of sides of a regular polygon, of a inscribed regular polygon increases, its area and perimeter approach that of the circle. And the little annoying box there will go away in just a second. Visually, the amount of, quote, of white, quote, space inside the circle is smallest with F, with polygon F. So take a look at this. So our answer here is going to be polygon F, and the reason is, again, F has the largest number of sides between A, B, C, D, E, and F. It has 10 sides. And as the number of sides of a regular inscribed polygon increases, its area and perimeter approach that of the, I guess we can specifically say, no, there we go. Are you not going to let me, I don't know how to get rid of that box. All right, you know what? That's fine. Oh, I want to, no. All right, you know what? It's fine. We could have said circumscribed circle, so approach that of the circumscribed circle, but the text box is being annoying, so I'm not going to bother with that. But anyway, our answer for 8 is polygon F, basically just simply because it has the largest number of sides, and so it's really starting to approach the circle, which you can see visually in this picture. Question 9. Given that the radius of each circle in the previous problem is 10 feet, all right, so we're told that, actually, I don't want to put it there. So I'll just highlight it, 10 feet. All right, so the radius is 10, and that is R. So the radius is R. Find the area of each of the regular polygons inscribed in the circle. List each area in the table below, along with the measure of one angle for each polygon and the side length of each polygon. One interior angle and one side length are given. All right. So with this question, we could either go horizontally or we could go vertically. And I might regret this decision, but I'm actually going to go vertically. So what that means is I'm going to fill out my entire column that says one interior angle. I'm going to go shape by shape by shape by shape and actually fill that in until that's done, and then I'm going to go back and do the length of one side. I just think it's going to be easier in general if we sort of tackle these not by shape, but by, what is it that we are finding. So for the triangle, we are told that one interior angle of the triangle measures 60 degrees, which kind of makes sense because it's a regular polygon and a triangle sums to 180, and 60 times 3 is 180. Now, for the square. Well, okay, I mean, it's a square, right? We know that an interior angle of a square is 90. So let's take the easy points where we can find them, right? Squares have right angles, so therefore the interior angle of the square is 90. Now, we could also calculate that, but we all know it's 90, so let's just put it and move on with our lives. All right, pentagon, here's where we actually have to start doing some work. So with a pentagon, as we've seen previously, any polygon can be divided up into a number of triangles. And the number of triangles for any polygon is going to be 2 less than the number of sides. So I could draw any random pentagon I want. It doesn't even need to be a regular pentagon. It could be any pentagon. So if I draw a 5-sided figure, I can divide that up into 3 triangles. And each triangle is 180 degrees, or it has 180 degrees in it. So if I want the total number of, if I want the sum of all of my interior angles for any pentagon, what I can do is I can say that my total is 5 times 2, which represents the number of triangles, times 180, because that is the sum for each triangle. And if I do this, I get 540. If I want the measure of one angle, which I'll represent with the Greek letter theta, I can take my total of 540, and I can divide by the number of angles, which is 5, because with a pentagon you have 5 interior angles, and 540 divided by 5 is 108. So for the pentagon, one interior angle is 108. I'll do that with the hexagon, and then with the octagon and decagon, we'll just go ahead and just give the answer. We'll do it one more time for the hexagon. With a hexagon, my total, the sum of all of my interior angles, well, a hexagon has 6 sides. If it has 6 sides, that means it can be formed from 4 triangles. It's always 2 less than the number of sides. So a 6-sided figure can be broken down into 4 triangles. Each triangle has 180. So my total is going to be 4 times 180, which is 720 degrees. If I want the measure of one of my angles, so we'll call that theta, theta is going to be my total, and they're all congruent, which means all I have to do is divide by 6. So 720 divided by 6 is 120, which means that for the hexagon it's going to be 120. I'm not going to show out the rest of them for octagon and decagon. Octagon is an 8-sided figure. So when you do all of the arithmetic, you get 135. A decagon is a 10-sided figure, so it's made up of 8 triangles. When you plug it into the same formula, you should get 144 degrees, and a circle is not applicable. So that's our first column. For the second column, the length of one side. Well, this kind of relies on a formula that we discovered in class. I'm not going to rederive this formula because it would, I think, just take a little too much time. If you're confused about sort of where this formula came from, I would recommend that you either go back and check the notes from class, or you could always come to office hours. So the length of one side, as we saw, so we'll call that L sub n. And in this case, n represents the number of sides. So our side length here is going to be 2 times the radius of the circumscribed circle times the sine, so we're using a little bit of trigonometry here, of 360 degrees divided by 2n. So here, n, again, is dependent upon the number of sides. So if I wanted to, I could maybe do a real quick column over here. N is 3, 4, 5, 6, 8, 10. And for a circle, maybe infinity, however you want to think of a circle. So now we just need to plug these in. And so we'll use our calculator to type these in. And remember, R is 10 in all of these cases, right? So we're told that R is 10, which means all we really need to do is just take this formula, 2R sine of 360 divided by 2n, and just keep plugging in values for n, and that will give us our answers. So I'll do a little bit of scratch work here on the right. So for move this a little bit. Okay. So for L of 3, it's going to be 2 times 10 times the sine of 360 divided by 2 times 3. Notice that that's where the 3 pops up in the denominator of my fraction for the sine function. 2 times 10 is 20. And then we want the sine of 2 times 3 is 6, and 360 divided by 6 is 60. Now, if we know our sort of some of our trig functions here, sine of 60 is root 3 over 2. So this is just 20 times root 3 over 2, which is 10 root 3. So our exact answer, if we were so inclined here, is 10 root 3. But we may also want to give an approximate answer here. And so going to the calculator, 10 times the square root of 3 is 17.32. So approximately 17.32 feet. Now, if your trigonometry skills or trigonometry knowledge, background, familiarity, however you want to phrase it, if it's not so great, you can also type in sine of 60. So we could also, just going back to the calculator here, if we type in 20 sine of 60 degrees, now the only thing we have to make sure though is that our calculator is in degree mode. So up here it says radian, so we have to go to mode, we have to go down and over to where it says degree, and then press enter. Now notice that degree is highlighted, plus the top of our calculator says degree. So if I press second mode to quit, and if I press enter, I actually get the same number. So depending on your class, depending on your teacher, depending on what it is that you're trying to do, if you don't know the sine of 60 is root 3 over 2, you could type in the original one and you'll get the same decimal answer. So it's really just a question of, sort of how clean do you want your exact answer to be, which is, up to the class and the instructions and all that stuff. All right, so I'll erase this because I just don't want to have a whole lot of scratch work here. For a pentagon, so now this is going to be L of 5, or L sub 5. Again, our formula is 2 times R. R is still 10. And sine of 360 divided by 2 times 5. Okay. Well, this simplifies to 20 times the sine. So 2 times 5 is 10. 360 divided by 10 is 36 degrees. Now, 36 degrees is not a special angle that we tend to sort of know much about in trigonometry, unlike 30 degrees or 60 degrees or 45 degrees. 36 is a quote-unquote random angle. I certainly do not know what the sine of 36 degrees is. If you do, then that's good for you, but I don't, so I'm going to go to my calculator. And we're just going to type in 20 sine of 36. Again, you have to be in degree mode, which we are. And if I press enter, I get 11.76. So going back. I guess in the interest of space, I'm not going to include the exact answer here, because the exact answer would be this. It would be 20 sine of 36. There's not a whole lot that we can do with that. So I'm actually only going to put our approximate answer here, which we found to be 11.76 feet. So exact is highlighted on the right, and approximate is in our table. For the hexagon, formula doesn't change, so L of 6 is 2 times 10 times the sine of 360 divided by 6 times 2. So this becomes 20 times the sine of 6 times 2 is 12, and 360 divided by 12 is 30. Now, 30 is one of those angles that if we are familiar with trigonometry, we may be able to actually remember what the sine of 30 degrees is. And it turns out the sine of 30 is exactly 1/2. It's actually a very nice, relatively simple number. And 20 times a half is 10. Right? So for the hexagon, our exact answer is 10. And we don't even have a rounded answer because 10 is 10. And if you're not that comfortable with the trig ratios, if we do 20 sine of 30 degrees, you'll get the same 10 that we just got. Two more in this column, and then we're on to area. An octagon has 8 sides, so L sub 8. 2 times 10 times the sine of 360 divided by 2 times 8. So we end up getting 20 sine of 2 times 8 is 16, and 360 divided by 16 is 22.5 degrees. So and we really can't do much with that. So, and I certainly don't know what the sine of 22.5 is. So I'm just going to jump right to my calculator here, and we're just going to do 20 sine of 22.5 close parentheses. We end up getting 7.65. So this is approximately 7.65 feet. And finally, for a decagon, I'll erase both of these at the same time. So L sub 10 is going to be 2 times 10 sine of 360 divided by 2 times 10. 2 times 10 is 20. Sine, again, 2 times 10 is 20, and 360 divided by 20 is 18 degrees. I don't know anything about the trig applications of 18 degrees, so 20 sine of 18 is 6.18. 6.18 feet. All right. Before we move on to area, I forgot to mention this with the interior angle. So just notice that with all of our shapes, as our number of sides was increasing, our interior angle also increased. 60, 90, 108, 120, 135, 144. And I don't know, maybe it's approaching something. Maybe if we did like 100-sided figure, it's like, well, what would that be? If we had 1,000 sides, if we had 1,000,000 sides, what would that sort of, what would that approach? So a good question to think about. Also, the length of one side, 17.3, 14.1, 11.7, 10, 7.6, 6.18, it's certainly decreasing. And again, think about, what would happen with 100 sides, with 1,000 sides, with 1,000,000 sides. How small is it going to get? So something to think about. Last column in this problem is talking about the area. Now, again, we saw this in class, and again, I'm not going to sort of rederive it because it would take a little bit too much time. But as we saw in class, we can find the area here by taking our radius squared, and then we're going to multiply by the number of sides times 2 trig functions. So it's the sine of 360 divided by 2n times the cosine of 360 divided by 2n. And that's how we can find the area for these figures. So we'll do a couple of these, but then I think in the interest of time, we might just sort of rattle off a bunch of our answers here. So for the area of the triangle, so area, we'll say A sub n, we should say. So A sub 3, our radius is 10, so 10 squared, times 3, times the sine of, I'm actually going to go, I'll go ahead and plug this in and sort of simplify it automatically. So 2 times 3 is 6, and 360 divided by 6 is 60. So this becomes the sine of 60 times the cosine of 60. If you're a little shaky on your trig, you could go ahead and plug this in, but you have to make sure that the 60 is inside parentheses. However, if we know our trig ratios, it actually turns out that this is going to be 100 times 3. The sine of 60 is the square root of 3 over 2, and the cosine of 60 is 1/2. All right. So we end up getting 100, and over here, I actually think it's going to be helpful based on the pattern that we're going to see. I'm actually going to evaluate this piece right here. I'm going to evaluate 3 times root 3 over 2 times 1/2. And we'll see what we get. So we're going to do 3 times root 3 over 2 times 1/2, and we get a decimal of about 1.3. All right. So we get approximately 1.30. And so I'm actually going to write that. I'm going to write 100 times 1.30. And just to make sure that I'm rounding correctly, we're going to multiply that by 100. We end up getting 129.90. So 129.90. All right. And this is feet squared. All right. We'll do the same thing with the square. With the square, so we want a sub 4. That's going to be 10 squared times. Now our n value is 4. And we want the sine of, so if n is 4, 2 times 4 is 8, and 360 divided by 8 is 45. And then the cosine of 45. So cosine of 45. All right. Again, if trig's a little shaky for you, you could evaluate this just by going to the calculator. 10 squared is 100. And then we have 4. The sine of 45 is root 2 over 2. And the cosine of 45 is also root 2 over 2. And I actually don't even need the calculator here because the 4 cancels with the 2's, and root 2 times root 2 is just 2. So this actually becomes 100 just times 2. And 100 times 2 is 200. So if you know your trig, and you know your fractions, and you know your radicals and all that other stuff, really for this question, you don't need your calculator. But regardless, even if you did use your calculator, you should get 200 square feet. Moving along. Pentagon. So a sub 5. Radius is still 10. N is now 5. If n is 5, we end up getting 2 times 5 is 10 divided by, or 360 divided by 10 is 36 degrees, and cosine of 36 degrees. Now I don't know much about 36 degrees, so I have to go to my calculator here. So I'm going to do what's inside the parentheses. So I'm going to do 5 times the sine of 36. You have to close your parentheses here. So if you've been doing all of this on the calculator so far, you have to make sure that that is closed after the 36. Then cosine of 36. It's a good idea to close the parentheses there as well. We end up getting 2.38. So this becomes 100 times 2.38. And again, just for rounding purposes, I want to make sure that I round this correctly. So times 100 gives me 237.76. So 237.76 square feet. 3 more and the circle, and then we're all done. So a sub 6, 10 squared times 6 times the sine of 2 times 6 is 12, and 360 divided by 12 is 30. All right. It turns out that this is going to be the last one where we deal with some nice trig functions. The octagon and decagon are not going to be as nice, so we're going to have to use the calculator for the octagon and the decagon. For the hexagon, well, 10 squared is 100. 10 squared is 100. And we end up getting 6 times. The sine of 30 is exactly 1/2. And the sine of cosine of 30, or rather the cosine of 30 is the square root of 3 over 2. It's kind of like the reverse of 60. And for our purposes, it's going to be valuable, I think, if we evaluate what's inside the parentheses, because we're going to see a pattern here at the end. So I'm just going to type that in, just what's inside the parentheses. So it's 6 divided by 2 times the square root of 3, also divided by 2. We end up getting 2.60 when we round. So we end up getting 100 times 2.60. That's a 0. And for rounding purposes, I want to make sure that all my decimals are lined up here. So we end up getting 259.81. So 259.81 square feet. And now for the octagon and decagon, we're going to be a little reliant upon our calculator here. You know, if we weren't already. So our area for 8 is going to be 10 squared times 8 times, if n is 8, 360 divided by 16. I think this was the decimal one. This was 22.5. So we're going to do sine of 22.5 times the cosine of 22.5. Let's go ahead and type in what's inside the parentheses there, which is 8 sine of 22.5, close parentheses, times the cosine of 22.5, and we get 2.82. If you want a sneak peek of pre-calculus, when you guys are in pre-calc, you'll actually learn that this is the same thing as 4 times the sine of 45. So same thing, but we're definitely not going to get into that right now. Regardless, no matter what you do, you should get 2.83. So we've got 100 times 2.83. And when we multiply that by 100, we get 282.84. 282.84 square feet. Last polygon, because the circle is not a polygon. So we have a decagon, so that's a 10-sided figure. 10 squared times 10. Now we plug in a 10 here. 360 divided by 20 is 18. Sine of 18, cosine of 18. I don't know anything about trig involving 18, so we kind of have to go to our calculator. Before calculators, you would have to look this stuff up in a table. Luckily, I never had to do that. Not that old. And we end up getting 2.94. So we end up getting 100, 2.94. We multiply that by 100. And we get an area of 293.89 square feet. If we wrap this up with the circle, we know that the area of a circle is simply pi times 10 squared. Now, notice there's really nothing preventing me from changing the order here. So I could say r squared times pi. So I could just say 10 squared times pi. And notice that 10 squared is 100. So it's 100 pi. And so if I continue my pattern here, I end up getting 100 times pi. That's a terrible pi. 100 times pi, which is 314.16 square feet. So we are now done this problem, and I would encourage you to think about what is happening to those numbers that I just highlighted as our shape gets more and more and more sides. Something to think about. Our next and last question in this assignment appears in the Go section. The directions say, use the given circle in the following problems to find the indicated measures. Part A, the circumference of the entire circle. Okay. B, the fractional part of the circle represented by the ratio of the central angle to 360 degrees. And then part C, the shortest arc length, AC, that is intercepted by the central angle. And they tell us that the shortest arc length from A to C is called the minor arc. A little bit of vocab there. The long distance from A to C around the circle is called the major arc. So we're looking for the minor arc in these questions. Question number 13. We have a circle here, a circle centered at B. We have two radii, A, B, and CB, and we're told that the radius is 2 meters, and we have a central angle of 43 degrees. And the first question is, what is the circumference of the entire circle? Well, this isn't too bad. We have a formula for this. So in order to find our circumference, we're given the radius, so we may as well use the version that involves the radius. And the version of the circumference formula that involves the radius is 2 pi times r. R is 2 in this case. And so if we clean this up a little bit, 2 times 2 is 4. So 4 pi. That's our exact answer. And if we want to give an approximate answer, we just take 4 and multiply by pi, and we end up getting 12.57 meters. And that's our answer, either exact or approximate. Part B, the ratio of the central angle to 360 degrees. So a ratio is just a fraction, and they give us our central angle. So this is really just asking, what is 43? What is 43 degrees divided by 360 degrees? All right, well, our degrees cancel, as they tend to do with ratios. Ratios tend to not have units. Well, actually, sorry, it depends on the ratio. But in this case, our ratio doesn't have any units. It's just a number. And 43 is prime, and it is also not a factor of 360. So we can't really reduce this fraction at all. That is as reduced, and we can get rid of the degrees if we want to. But other than that, we can't really do much with this fraction. So it might be good to get a decimal answer here. So 43 divided by 360 is 0.12. So our approximate ratio here, so approximately 0.12. That is our ratio here. Part C says the shortest arc length AC. So just to see this visually, when they talked about the major and the minor arc. So the minor arc is this piece right here, right? That's AC. The major arc, which is not what we want, but just you might see it in the future, the major arc goes in the other direction, like that, right? So the minor arc is the smaller one, and the major arc is the bigger one. Typically, in order to refer to the major arc, if you wanted to refer to the major arc, you would actually need another point. Actually, let's do this. So you would need like another point on the circle. Maybe we'll call that point like D. And then the major arc would be something like A, D, C, like that. And that would be referring to the major arc because you start at A, you go through D, and then you end at C. But anyway, that's not what we want. We want the minor arc, which is just AC. So notice that, let me get rid of all that, just extra stuff. There, all right. So the arc length AC, well, all we have to do here is we just need to take our ratio, which our exact value was, let me do this in black. So our exact ratio was 43 over 360, and we want that much of our circumference, and our exact circumference was 4 pi, right? So here all we're doing is we're taking the ratio of our central angle, essentially how much of 360 are we talking about? We're talking about 43 of 360. And we just apply that ratio to our total circumference, and that will give us the arc length AC. Well, we can actually simplify this a little bit. So 4 goes into 360 90 times. So this becomes 43 over 90 times pi. And if we want, so that's actually our exact answer. But if we want to give an approximate answer, we can just simply type this in. So 43 divided by 90 times pi. And that gives us an answer of 1.50. So this is approximately 1.50. And I guess I forgot my units here. We're talking about meters. So let me just, you know what? I'm just going to erase it real quick. So this is 43 over 90 pi meters, which we just found is approximately 1.50 meters. And that is the length of our minor arc AC.